Welcome back to The Explainer. Today, we're putting on our forensic data science hats to look at how advanced algorithms were used to restore one of history's most fiercely debated pieces of footage. We're taking a strictly computational, no-nonsense approach to a highly degraded historical artifact. So, the 1967 Patterson-Gimlin film, we all know it, right? Most of us have seen that iconic, incredibly shaky footage of a bipedal figure walking through the woods. But listen, today, we aren't here to debate the myth. Instead, we're going to dive into the genuinely gripping process of mathematical data restoration. The big question is, how exactly do you take half-century-old, heavily degraded film and apply modern computer science to it without, accidentally injecting your own human bias into the results?
Here is our roadmap for today's explainer. First, we'll look at the Patterson-Gimlin film problem. Second, multi-sample frame compositing. Third, algorithmic motion stabilization. Fourth, real math versus generative AI. And finally, we'll get an unbiased look at Patty.
All right, let's jump right into section 1, the Patterson-Gimlin film problem.
So here's the kicker. The original camera reel, it's completely lost. Because of that, researchers have had to work with multi-generational copies. And these copies are rough. They are plagued by random film grain noise, severe physical scratches, and these huge white pockmarks. The actual underlying detail of the image is literally buried under generations of physical decay. To fix this objectively, and by objectively I mean without a human just manually painting over the image in Photoshop, scientists used a very strict computational workflow. They meticulously digitized 8 independent, high-quality prints using a 12-megapixel DSLR camera. Then they computationally aligned the frames, merged them together to eliminate that noise, and finally mathematically stabilized the whole thing.
Moving smoothly to section 2, multi-sample frame compositing.
Okay, the absolute core concept we need to understand here is the signal-to-noise ratio. Whenever you're dealing with degraded data of any kind, you have to amplify the true signal, which in this case is the actual physical image detail captured by the camera lens way back in 1967, and at the same time, you have to suppress the random background noise, like the film grain and the physical damage that accumulated over the years.
Think of multi-sample compositing kind of like a mathematical voting system. If a random scratch or a piece of dirt shows up on one copy of the film, well, it simply loses the vote when it's averaged against the 7 other intact copies of that exact same frame. The algorithm effectively fills in the missing data by summing up the image data from the rest of the group. It's actually a beautifully elegant solution.
The visual difference this makes is honestly night and day. By running this exact mathematical optimization across the frames, researchers successfully reduced the mathematical error by a massive 87%. They essentially erased all those physical scratches and static, and they did it without faking a single original pixel. Which brings us to section 3, algorithmic motion stabilization. Now we have to tackle that iconic erratic camera shake. To correct that objectively, they brought in the SIFT algorithm, which essentially acts like a digital fingerprint scanner. The algorithm mathematically identifies and matches thousands of static background key points. Think of things like the specific shape of a fallen log or a unique tree branch, and it tracks them perfectly across the different frames. Once those digital fingerprints are found, they use another algorithm, called ransack, to filter out any bad matches. This allows them to solve for something called homography. Now, in simple terms, homography calculates a really complex